How do we train large language models? How much thinking steps do we think usually R1 takes? First, even before entering into how to build better reasoning models, let's understand what is reasoning. Hi all, I'm Sachin. 2 months ago here I gave a talk about building reasoning models. It was more speculations at that point because we didn't have R1 and Kimi, but now we have more data, so I'm just enriching that talk, adding bunch of more details, removing some things and this thing. I'm Sachin, I'm part of batch 2 of During's Dream, aka now Lost Funk, and yeah, so this talk is about building better reasoning models, state of the art and beyond. So I'm going to explain what happened with DeepSeek R1, Kimi K1.5, and beyond is I just want to throw away some of my speculations that what all problems which still aren't solved and where we can get better reasoning performance. So yeah, first even before entering into how to build better reasoning models, let's understand what is reasoning. Does anyone know what's the country code for calling Mongolia? No one. And no amount of additional time is going to help you to come up with that answer. You either know it or you don't. But does extra reasoning, extra thinking time, does that actually help LLMs? DeepSeek R1 shows us that with RL training, as with steps increase, as they go beyond 8K, or even as they're increasing, the average response length increases. And while average response length is increasing, its performance on AMI, which is USA Math Olympiad benchmark, the performance also keeps increasing as model figures out it should use more and more time to solve these problems. How much thinking steps do we think usually R1 takes? So on open thought data set, they showed that almost there are lots of responses which contains more than 20,000 tokens. A single page usually contains around 500 words. So 20,000 tokens is almost 40 pages worth of reasoning traces. And there are, as we can see, lot of problems where R1 generates that much length of reasoning tokens. So how to do reasoning? People have been doing it since last 3-ish years on lot of different things. First Galactica showed us with work tokens, and even before around the same time people tried with let's think step by step sort of prompting. They showed another way was few short chain of thought examples, and then large language models specifically GPT-3 was able to do some sort of reasoning. Galactica showed with work tokens, someone came up with scratch tokens, but it's the same thing where you allow model to do some sort of reasoning work and then generate the answer rather than point blankly giving the answer. And by using RL or such, we'll go deeper into RL a bit later. So even before we go into reasoning and all of those things, I just want to take a step back and talk about how do we train large language models. We start with a huge amount of pre-training data set, do some sort of self-supervised learning on top of it, and come up with a base model. This is Llama 2's recipe, but this recipe is constant from Llama 2 to DeepSeek R1, and even before that ChatGPT, InstructGPT, the recipe is the same. We start with lot of data set, do self-supervised learning, come up with base model, do some sort of supervised fine-tuning, get an instruct model, and then do on top of it some sort of RL fine-tuning. It can be RLHF, RLAIF, or now RLVR, which is RL with verifiable rewards. So this is in general, this is the kind of pipeline used to train almost all the LLMs. But people have been trying to do RL on top of base model since last few years. But those experiments didn't work as much as well as DeepSeek R1 did. The reason behind that is the performance of base model. Kimi paper's appendix explicitly states this thing that RL efficiency is closely tied to the performance of underlying base model. This is somewhat obvious that if your base model is not strong enough, then RL, we can of course do tabula rasa learning where RL figures out all of these policies completely from the scratch, but that RL with this thing is kind of expensive. If we want to start without any basic priors, any sort of biases about how to solve that problem, the problem becomes extremely hard and we will just require huge amount of compute. So like we'll just take a small overview of like how DeepSeek V3 and Kimi base models are trained. Like DeepSeek V3 is trained on 4.8 trillion tokens. Like both of these base models have larger amount of code and maths as well as other reasoning data like puzzles and some other amount of kind of reasoning data. DeepSeek V3 has vocabulary of 128k with like a byte level BP tokenizer. Kimi, we don't know any of these details about base model. They just tell us about how they are sourcing their data, like what's their data composition, and like how they are pre-training it, like what are the different steps of pre-training. But they don't give any more details about that. DeepSeek V3 uses multi-token prediction loss. It's a 671 billion parameter mixture of experts model with 37 billion active parameters for each token. They show large scale FP8 training for the first time, and they use AdamW optimizer as well. So once we start with base models, can we perform directly reinforcement learning on top of that while skipping the SFT space completely? That's what DeepSeek R1 did, and that's the reason like this thing was so cool that without using any supervised fine tuning or anything, they just put this particular neural network in front of some sort of simulator where like it got a problem which is like the initial prompt, it generates the like reasoning traces and generated the final answer and got the feedback from simulator, which is like here there are multiple verifiers which kind of gave the reward. And like this is the first time at this high scale base model LLM plus RL for the first time worked. After that, like bunch of other papers showed that this also works. A lot of people like did these similar experiments on much smaller scale as well, from like 0.5 billion, like 500 million like parameter models and all of those things. And people figured out, okay, if you start from a strong base models, directly doing RL simply works. Like it achieved great performance on multiple reasoning tasks, but at the same time, the resulting checkpoint, the resulting model was not as much usable for normal tasks where we ask it some random questions, like that persona which we have with Claude Sonnet or ChatGPT, that was not there. It was able to do great on math and science questions, but otherwise it was not that great. And the major problem here was like sometimes in the reasoning tokens, model used to switch the language, it used to generate some random noise and all of those things. That was some problem. But another beautiful thing in this particular pipeline or in this particular experiment was, in some of the answers there were some aha moments. They call it aha moments because like model, like without explicitly teaching it to verify its outputs or like think about some other ways to solve the same problem. So like after this, like we talked about this, like let's go back like to the supervised fine tuning. The thing is, what we talked about with R10 was that it does language switching, or there is some garbage in reasoning traces which comes as well. And if we as a humans are like going through these reasoning traces and we want to guide them or understand them, then that's a like bad format from like usability point of view. So that's the reason like a supervised fine tuning can be helpful there. We talked about like Galactica paper which introduced work tokens, this Scratchpad paper which introduced scratch tokens. These tokens are literally like, these are the examples where input prompt comes, model figures out, okay, these are my thinking tokens or work or scratch tokens. I'll do the work here and then output the answer. But like this is again slide from the last presentation. At that time we didn't know how RL comes to exactly to the rescue, but now we know with these papers how RL comes to the rescue. So major problem with like explicitly generating these scratch tokens, work tokens or reasoning tokens is internet data has reasoning steps, but it often misses steps in between. We usually, when we are solving the problems, we automatically jump in between steps. We don't do all of the minute things by ourselves. And like not having this entire thought process kind of like confuses the models, and like it becomes harder for models to follow them. And like generating all of these things manually is very much expensive and it is hard to scale. But there are still some advantages of SFT. This paper, like which is like SFT memorizes, RFT generalizes, it shows like in two different tasks. One is like textual gaming tasks and another is like visual tasks. It shows that SFT is helpful for RL training because SFT stabilizes outputs model format like this is where thinking tokens should come, this much amount you should usually spend on those tokens and all of those things. And after that, RL enables to generalize across like somewhat out of domain performance, out of distribution performance as well. So in a like visual task in that they show that with SFT you kind of reach the success rate pretty fast and it plateaus. With RL it takes lot of time, but eventually RL plateaus. But when you are training with RL, even for out of distribution tasks, like RL performance doesn't go down by that much, but same with SFT, it success rate drops significantly. But by the way, this is RL, but only for, they have done experiments with RL where rewards are outcome based, not process based. So I'll just talk about how Kimi paper did SFT and versus how DeepSeek did SFT. So Kimi used like 2 million text, 2 million examples. 1 million were like just text, which is like this is the this thing like configuration of them, like 500k in general QA, 200k in coding, 200k maths, 20k long context tasks, like that, and 1 million is like text vision examples. Like quality and diversity of RL prompt set play a critical role in ensuring the effectiveness of RL. But like to be honest, like quality and diversity, it's gonna be true for even SFT as well. So like I think this should be the like true across like any dataset generation, that quality, diversity are like the most important things. They like to generate these 2 million examples, like they start with like high quality human annotated data. I'm assuming it is going to be few thousand of examples, and then from that they use this example to generate more and more synthetic generations, and then like hire some annotators to kind of like rank, okay, among these 10 generated outputs which is of the highest quality, and like that they seed it to like 2 million. And yeah, like the pipeline for Kimi is like they start with base, do SFT with these 2 million examples, then they do long context SFT with like these might be few million, like few thousand examples, but they haven't explicitly said that how many long context SFT examples they did, but they mentioned that it's a light fine tuning. They are not like doing like full fledged fine tuning here. And actually this paper also talks about that if you like create a very strong instruct model, that kind of hampers RL training, because now your model is in like some sort of local minima where like escaping that region and like going and finding good policy becomes much harder. So I'm guessing that's the reason they are doing like few thousand examples and like light fine tuning, and then they perform RL. Like their RL is slightly different than DeepSeek's RL, but we will go over those details like across the slides. Yeah, so they start with some cold start data set to just ensure that model formatting is proper, like output formatting is proper. Like they generate this cold start data set by like few shot prompting like base model with long COT demonstrations, and like prompting models to generate like it's just like whatever we saw in previous prompting techniques, same like few shot COT, like think step by step and ask it to like verify and like do some reflection and all of that, like the sort of prompts, plus like otherwise filter and manually edit like DeepSeek 01, like DeepSeek R1 0 responses. Like after like RL training is done, so in the DeepSeek, like this training pipeline is like you start with base model, do some cold start fine tuning, then do a strong RL like fine tuning, like RL training, like which goes closer to the performance of R1 0. Once you do that, then you again do some SFT, and then you do again like RL with verifier plus reward models. So like this SFT, which is like post RL SFT, this is like around 800k examples for 2 epochs. So like Kimi had around 2 million examples, these guys have like 800k into 2, so around like 1.6 million, so something in the similar ballpark. Here they have 600k reasoning examples, which are like which contain some amount of like reward model verified queries also, and 200k non-reasoning examples, which is chain of thought as like Paris temperature, like those sort of the examples, plus simple hey like how are you doing and some sort of those things. So like a generic slide about why, like what is supervised learning, unsupervised learning, hot dog versus not hot dog, supervised learning, RL, like these are the 3 major like properties of RL that there are no correct actions, just rewards. So in supervised learning, we have like the correct answer. In RL, we never have correct action. We just sample one of the actions which from available actions and we evaluate that particular action in that particular state. So rather than instructive, here we have kind of evaluative feedback. Second is episodes last for many steps. SFT is usually like a single step. In RL, you usually get rewards occasionally during the episode. So you have a credit assignment problem. As we talked, like as you asked that question, that like what if reasoning stresses go wrong? So in RL, like we never usually know, and we kind of like figure out that okay, these intermediate steps have usually been associated with intermediate steps or like states have usually been associated with higher reward down the line. So because of that, this state should get higher reward, like higher value, like that, and that like these two like evaluative feedback and credit assignment problem are like the biggest issues. And third is like points are usually like in supervised learning, all the points, all the examples are IID. In RL episodes, all the state actions, they are not IID, they are like extremely dependent on each other. This is in general the diagram that environment passes on state and reward and agent gives action, and these loops keep on going till the terminal state is reached. And we will now talk about like what can be the states, what can be the actions, what can be the rewards with respect to specifically like the reasoning problems. So what are states? Like I personally like to think about the way we solve these reasonings or the way we do RL with LLMs as kind of bandit setting, because like the non-stationary part of environment is technically not here. Like from environment we are getting the prompt, but after that all of our actions kind of change the like, if we consider state as like all the prompts or everything we have seen till now, it changes, but it doesn't, environment is not changing anything. So we can consider our actions as rather than the complete answer rather than individual tokens. So it can have like different like we can look at it in both of these settings. So in bandit settings, you can look at states as just a prompt and action is the entire response. In RL setting, we can see that okay, no, prompt is a state, then whatever answer, like whatever token model generates becomes part of the state, and like such that the state keeps on evolving. Like these both are, I think, fine like approximations of the underlying MDP, and like thinking about these both approaches can help us like tweak some hyperparameters, and that's the reason I'm including them here. So what are the actions? Same, like in bandit setting it needs to be complete generation. In RL setting we can do lot of different things where like we can consider actions as finite set, which can be vocabulary, and every like action, like every token we generate, if we have some extremely fine-grained process reward model, like process reward model or process model, then generating each token should get its own credit assignment, it show its own some sort of reward, like probably not naturally but some sort of like through either value functions or something like that. Like infinite action spaces can be like either every thought or sentence can get its own reward, and we can consider that as an action, or like as we currently look at all of these things as like complete generation is an answer, and like we give reward just at the end with like outcome based. Where do rewards come from? Like either your LLM can generate lot of different answers and do majority voting, so that is just an ensembling approach. Another thing which is generator generates multiple answers. Either we do RLHF where a human sits and like okay, this was amazing, this was not, or this was better than this, that sort of ranking, or we do RLAIF, or like Anthropic you like to call it like constitutional learning or this thing, where we rank those approaches, rank those things, or we have some sort of external verifier, like which like as we talked about this thing, like in case of code it can be you generate unit test cases and figure things out. For specific math problems we can either do some formal like theorem proving things, or we can again like over here also we can do like a reward model for maths, which is what Kimi paper did. And like there are majorly like these three approaches for like where we can extract the reward from. Like this is a really good paper about, this paper mostly talks about like ensembling and like what happens if we keep sampling like different answers, and like if we have a weak model and if we keep sampling more and more answers, like our pass at like n that like might like increase, like we will get some win rates, but majority voting might not give you better performance and performance might even drop down. So this paper talks about that indefinite accuracy improvement through resampling. We have a weak model, we sample it like a million times. It like if you have an amazing verifier to identify, okay, this answer was correct and this, it will scale, and that's what like rejection sampling does. It will work. But if your verifier is imperfect, then performance might degrade with like weaker models, and you need to have better intelligence in the model itself. You might need to have stronger model. And like this is the major question, that can we have perfect oracles which gives us the reward in like the, I'm gonna call it traditional RL, but like with specific simulators we had like reward coming in from simulator. Here we are kind of approximating rewards with like all of these things, like either majority voting, ranking through either humans or LLMs, or doing some verification. We are approximating the reward. So can we have near perfect verifiers, or like how can we get to the perfect oracle? This is like a major research question, and that will help us like build even stronger models. Kimi paper discussed how they designed their verifiers. So for coding tasks they use I forgot that specific library name, but they use that library to generate lots of unit test cases and like ensure that LLM passes all of them. This paper talks about that if you are not careful with the generation of your unit test cases, then sometimes your test case won't like have the perfect coverage, and you might end up settling for like worse outputs. And like for maths, like this paper like trained some sort of reward models, like which are chain of thought reward models, and they worked pretty well. Of course, like when we are using reward models, the risk of reward hacking does come into play. So like we'll talk about reward hacking right now. Like Goodhart's law, like when measure becomes a target, it ceases to be a good measure. Or like in like here, when we generate lot of test cases, those test cases tell LLMs, okay, we should evolve. But if those test cases are somewhat faulty, or if they don't have like complete coverage, LLMs might get a wrong signal, like because rewards is the major, like is the only source of signal. They will get the wrong signal, and we will optimize for something which is not correct. Something we might optimize for wronger like path. Like we have seen this with like in general like normal model training, where like in long form QA it figures out how to use consistent logic for incorrect answers, or like these things, coherent answers with subtle fallacies. Another, a real world approach of like reward hacking can be the way, like at least I used to write my SSC exams or like my school exams, where you write longer answers with like good handwriting, you get better reward. It doesn't need to be accurate. Like humans do that, like LLMs also learn from in the same way. Like I won't go into the details of reward hacking, but like Lillian Banks, this particular post is amazing for that. And like Karpathy's this tweet which compares RLHF versus RL, even talks about like how reward hacking can happen. And one of the reasons we don't like keep increasing number of steps when we have reward model as our source of like ground truth or source of rewards is like we usually do 1 or 2 epochs maximum. Is after like more epochs, RL forces the model to converge to like hack the rewards. Reward shaping, like structure of rewards. This is like basically where do we get rewards? Like if we get rewards exactly at the end, that's like accuracy based rewards, or like format length rewards, outcome reward models. They all like give you like all the credit assignment exactly at the end. So in case of chess games or like Go games, if you get reward exactly, like if you either win or lose, that 1 or -1, or like in case of stalemate probably 0, like in those cases like that would be this. But if we give some sort of like chess points, that okay, if you capture someone's like queen you get like 8 or 9 points, if you capture the rook you get 5 points, if you capture pawn you get 1 point, if we add those in as a rewards in between, then that can become process rewards or process reward models. Like as we talked, like advantage of having process reward is you can converge faster. These give you like nicer biases to learn faster. But again, you will like reach to suboptimal policies because like your agent might learn that okay, capturing opponent screen gives me those 9 points. Like let me just do that while losing the game. So that's a risk. Quen released this like really good paper about like process reward models specifically for mathematical reasoning on maths. This thing like they showed that like there are basically three like, to be honest, like mostly people use this Monte Carlo estimation as a process reward strategy. So Monte Carlo is like you run the entire thing, you get the reward at the end, and using that reward at the end, you kind of heuristically give some sort of reward to the intermediate steps which came before that. So like that is Monte Carlo estimation of like giving process rewards to intermediate states. They show that like there are limitations to using Monte Carlo estimation, that we can most of the time have wrong credit assignment happen, as he said, like when the reasoning traces are wrong but the outcome is correct, you give like good rewards to those traces as well, and that becomes a problem. Also when we are sampling multiple times, like if some of those reasoning traces, wrong reasoning traces get better reward, then like in general scores get inflated, and when we are doing some sort of search mechanism, we end up exploring the wrong paths of the like tree. And like maximum rewards usually, like when we are doing MC estimation, are given to the last steps, which essentially becomes again outcome based reward models. They showed that like stringent data filtration with Monte Carlo, and along with using LLM as a judge, that okay, how important this particular step was, and such sort of like prompting, these things kind of helped them, like specifically only for mathematical reasoning. How to do process reward models for other reasoning, it's still an open question. Reward engineering. Show me the incentives and I'll show you the outcome. Like Charlie Munger said that, and like in RL it's the most true thing. Like everything else, like how you design your rewards, how you like, we will see later in our different algorithms, like literally how people manage those rewards, how they massage those rewards kind of changes the algorithm, like changes algorithms. So we can add multiple sources of normalized rewards. Like usually like people add multiple rewards, but you cannot just add rewards, because like if the ranges of reward is pretty different, then one sort of reward can overshadow like all the other ones. DeepSeek R1 uses accuracy plus formatting plus language consistency. Kimi uses negative length reward or like kind of length penalty to have like smaller reasoning chains. T1 uses entropy bonus for adding diversity, also gives penalty for garbage text and like repetition. We can experiment with different nonlinear transformations with mixing these different like reward sources, that in this specific, and we can add these rewards like as specifically Kimi did this like negative. You train your policy with specific rewards. Once your policy achieves certain performance, then you can add additional rewards to like redirect in some other directions. We need more verifiers, like also simulation environments. Like after DeepSeek's paper, this was Karpathy's tweet. For friends of open source, in my opinion, the highest leverage thing you can do is to help construct high diversity RL environments. Like different verifiers across different environments. Like we have for coding, we have for maths. Can we do some sort of like reward models for like taxes, for auditing, for legal reasoning, like for puzzles, for like automatas? Like there are a lot of these things, and like those things will help, because then we can literally pick and choose, okay, this is our base LLM, we pick up these 5 like environments because our end user or end customer cares about these properties, only train on those 5 simulations, and we get much better model at the end. For these open source resources, like Nous has like a collection of reasoning data sets. They have around 95 tasks across like from algebra to puzzles to like lots of different things. TextArena.ai, this is also something interesting. They have generated around 30 textual games to like, so that LLMs can play against other LLMs. This is mostly for evaluation, but we can think of like, we can convert this to actually like add capabilities to LLMs as well. Like someone just recently did LLMs to play the codenames game. So we can have like a lot of those sort of experiments. OpenThought has like open source reasoning data sets, like they have like around 114k examples from R1, and there are like lots of other examples like Hugging Face, like this update R1 which came yesterday. They list around like 5 to 6 other different data sets for the same. So for India specific, like what we can do is like probably Indian legal arguments or like tax and compliance, like we can generate like reasoning traces for solving like India specific tax questions, that okay, how these reasoning traces can work or something like that. Now we will enter into the like methods, usually like RL methods, and here I am talking only about like reinforcement learning where gradients are flowing. We are not talking about search or dynamic programming. They are usually classified into these two like families, value based and policy based. Where value based and policy based interact with each other, we get kind of actor critic. Usually like PPO, GRPO, all of these are policy based ones, and we use policy based because like they don't have theoretical guarantees that they will converge to the optimal policy, but they usually converge faster. And because like in deep RL we are anyway like RL is sample intensive, we have high, like we require large amount of samples, so any algorithm which gives us better sample complexity, we use them. So usually we go with policy based. So PPO versus GRPO. DeepSeek's major like not major, but one of the contribution was they used GRPO. Like if you look at like this is GRPO, this is PPO. If you look at this particular equation, and please like for now ignore this scale divergence penalty, this we add in PPO as well. If you look at both of these equations, they're to be honest almost same. There is minute difference, but they're almost same. So here we do it for like we need to add a separate head which like kind of predicts value of at every state, that okay, what would be the value of this particular state. We need to add that like value head, and we need to keep training that value head. So like keep training, or we need to train that value head, and that adds additional complexity. And like DeepSeek didn't want that additional complexity, so they used this something amazing, which is like as you have already these multiple generations, we can compare these multiple generations against each other, subtract the mean of all of those generations and divide by standard deviation, and that gave us like GRPO. So this is the policy gradient theorem. This is like, this was I think found in 1992 or something like that, and all of the like these algorithms are descendants of this thing, where like we take log probability of like policy, like log of policy, like those specific log probability of that state and action happening, multiply that with the Q value of that state and action. So this Q value is like expected, like when we see this state and action, what's the future estimation of reward. And like our job here is to do gradient ascent. We want to improve this number as much as possible. So we change, like this number is in our control, this policy is in our control, like that's the theta. So we like change that theta such that like this should keep on improving and improving. So this is the general policy gradient theorem. If we change this estimation with a Monte Carlo estimation, that we run the entire episode, get that specific return, plug that in, that becomes reinforce. The major problem with reinforce is because in some episodes you are going to get really good rewards, some episodes you are not going to get much reward. So you get like really high variance. To remove that high variance, people started to like subtract it by some sort of like baseline. Initially that baseline was some constant, later people started to learn that baseline, and that became like reinforced with baseline. After that people figured out, okay, rather than subtracting by some random baseline, a specific baseline really works well, which is value function at that specific state. People did something called natural gradients. So like it wanted to have like some trust region, because our updates sometimes like went pretty far from this thing. So they did specifically this clip was their major contribution, where they clipped the return like within some specific epsilon, that if there is like too much variance, they clip this, and here we replace log probability with like ratio, probability of the current model versus the previous snapshot. GRPO is similar, where just our advantage becomes this thing that the reward which we saw versus mean of all the rewards in that group divided by standard deviation in that group. The policy mirror descent which Kimi uses. So this is again log, like derivative with respect to log probability multiplied by, but here rather than using just reward, like rather than using advantage function, they have used this specific thing called R cap, and R cap is again mean. Along with that, they add this specific additional term which is to like keep the policy near the previous policy with log of like the current policy divided by previous policy squared. They do this and like they again weight this with a temperature parameter. Like Kimi does another amazing thing which is about sampling strategies. They use curriculum learning which DeepSeek doesn't, but DeepSeek does a completely RL training. These guys do some sort of SFT and like they have much more like they have done much more detailed work about like this thing probably. Plus they might have lesser number of GPUs versus like DeepSeek. We don't know exactly how many GPUs they had and like what's their training cost looked like. An interesting thing which both of these papers did is distillation. Kimi's distillation is about like distilling long chain of thoughts into shorter chain of thought so that you don't spend too much like compute at inference time on generating that probably like 40 pages worth of reasoning traces. So like they did this with like multiple approaches, model merging, rejection sampling, where you generate multiple chains of thoughts and figure out okay which chain of thought is correct and shortest, and then SFT on only those. DPO and RL with length penalty. RL with length penalty saw the minimum performance degradation. Like training smaller models, like what Kimi showed and like what they told us specifically with all of these things is training smaller model with longer context length might be as performant as training bigger model, and DeepSeek's like line is exactly opposite of that, where they say that like training smaller model was not as performant as just distillation from bigger model. So I think like because their pipelines are so much different, they are getting these different kind of underlying behaviors. DeepSeek talked about distillation to smaller models, and like distilling the logits into smaller models worked wonderfully with like DeepSeek R1. Like it's a great model, so like this performed really well with distillation. But they also said that they haven't done any after like distillation RL experiments, and that's still an open research question which community should take up, is what they said in their paper. This paper came today and like I just wanted to add this particular slide because it's extremely simple. Like just to get better performance, they kept adding weight at these things like before reasoning ends, so that model explores more and more, and just adding that simple hack gave better performance. This is in general search, but like probably we shouldn't sleep on search. Like having search and like rather than model figuring it out itself that how to add alternatively, if we can add some sort of search methods in it, we might be able to get like much more better performance, like much more efficient model training. How to do that, it's still an open question. They trained LLMs to play chess with search. Like 2 months ago we talked about this, and I thought like O1 might be doing something similar like that at that time. Now probably it feels like they are not doing something similar. They just figured out how to scale RL rather than search, and like it just works really well. And you can like the search former paper did that, like how to internalize that search in context length. They showed that in that specific paper. Like now it's just last part of some of my speculation. So problems with agents, like Mike Knoop, who is co-founder of Zapier and ArcAGI, like co-founder of ArcAGI as challenge as well, he's like the number one issue preventing more adoption is low reliability or consistency, like these things. And if we can make things more reliable, like people will figure out how to make those things more accurate. My like hypothesis about why things are less reliable right now is like today the way we build agents is like we just do prompting. We don't do any fine tuning, no gradients flow, nothing. We take the like APIs or normal LLMs. The point is exactly like we do it with prompt way, and like we extract things from like databases, and like when something works once, we expect that thing to work for all the other use cases, something like that, where user prompt changes a bit, as he said, like in that reliability, user prompt changes a bit, the content of databases change quite a bit, the function calls which we do change somewhat, and like that's the reason agents don't work. And like my speculation is, if we keep doing generating these RL based simulations, like we might get much better like agents. Uninterpretable vocabulary is like the coconut paper which came, like we talked about it last time, but like rather than having reasoning in specific like token space, like if we just pass the like unembedding layer as like to the next, like as the next token, like and allow the models to reason, like it still does it does much better. This was like Meta's paper about coconut, and like if we can scale compute even more, probably like, and if we don't need user understandable reasoning processes, then like these things, like this might be the way to go. And thanks a lot.